So it is 17:10. So we start for our first two by the assignments. This is on week 5. Okay. Start with the assignments for week 5. Okay, so this is the welcome to this session. Good evening, everyone. Welcome to this session of problem solving and outline session of number 6. Course MA 91, that is production technology theory and practices. Okay, production technology, that is theory and practice. Okay. Production technology, it is theory and practice. Okay, so this is the sixth session now. So we first start with the fifth assignment. Okay, so this is the first question for fifth assignment. 15 millimeter by 15 millimeter cantilever beam being subjected to a normal force 200 Newton and subjected multi the strain multiplied by 10 to minus 5 measured by the strain given at a distance of 20 Newton from the point of application of the force will be. We want to find the strain here. So we know what is the formula for strain. It's simple again. Okay, we know the formula of strain. Okay, what is it? Is equal to, that is E is equal to 6F, then that is our distance divided by E into B into H square. Okay, so what is our F? F is given here. Okay, so we have your F. F is given here 200. L is given, which is L actually. L is given 20. Okay, what do we have here? We have F, which is equal to 200. We have L, which is equal to 20 millimeters, and we have B, which is equal to 15 millimeters. We have H, which is equal to 15 millimeters, and we have E, which is equal to 200 gigapascal. This is E, which is 200 gigapascal. So just put it in this formula. So what will be your answer? Just put it in everything in meters. Okay. So just start writing. So it will be 6 into your force. It is 200 into 20 into 10 raised to minus 3, because the distance, the length is in meters. Okay. So we kept in meters into what is your E, which is equal to 200 gigapascal. So it is 10 raised to minus 20 10 raised to 9. 10 raised to 9 into what is your B, 15 into 10 raised to minus 3 into your h square, that is 15 square into 10 raised to minus 6. Okay, I told you already. So the answer we came by, it is 3.56 into 10 raised to minus 5. But what they asked here in question, it is weight. The weight is defined, it is multiplied by 10 raised to minus 5. So we can't write 10 raised to minus 5 there. So your answer will be 3.56. Okay, this is only your answer as per the question. So this will be only your answer. This is your strain. So in impact dynamometer, the tangential force is measured by the gauges placed at angle of degree with respect of to the vertical axis. So you know this is the vertical axis, and we have this kind of ring gauges, and we know at what value this angle will keep. Okay, this angle is, you know, this given the slides that this angle is 39.6, okay, and this axis, okay, with vertical, and this is the angle. Okay, this is the angle. This also is correct. Okay. The relationship between magnitude of cutting force and reflection in the dynamometer is called, this figure, it is simple definition is there. It is given in the slides that it is called as inertia. Okay. The resistance. Circular ring structure by itself are not useful for dynamometer due to its instability, because in previous time I also show you that in assignments. So that this kind of force is required, that is Ft. like some tangential force is Q or F. This kind of tangential force you will got. Okay, this kind of force if you got, what will happen? It will start rolling. This is your base load, the point at which it is connected, load connected to this. Okay, this is the point at which it is connected to the base. If this force happen mostly, the RP that is there FT, your tangential force is there, and your thrust force is there, and your this will be at first force that is going to be T, and this is your tangential force, is called as FQ. For T, you can consider this is FT means thrust force, FQ is your tangential force. Okay, so if this force would apply, what would happen? This may try to roll. Okay, this may roll here because of this force. Because there is only one living load. Okay, the chances of rolling is very high in this case. So it's called as instability because of the chance of rolling. Okay, insufficient base location is wrong. Insufficient rigidity is wrong. They are enough region because we are calculated by calculation. So they are enough rigid. Tendency to buckle is not there. Calculation is not counterproductive, but the insufficient base location is again wrong. But the main problem is only the instability because it may roll. Okay, the rolling is the most important problem here. That's why we can't take it. We can't take it. Okay, rolling is the most important thing. So the answer will be instability. It's correct. Okay, because of the rolling part of it. For the tool creator where the mechanism of primary responsible. Okay, in the previous assignment told that diffusion is primary because the speed is high and due to high temperature is very high due to high temperature there is a very high temperature and due to high temperature the it is shown that instability. So for tool creator where the mechanism of where primary responsible is. It's called as diffusion. Okay. In previous assignment, I also told you that previous session that diffusion happen because of high temperature. In those areas, there is a very high temperature. Okay, due to very high temperature, the diffusion process it got increase. Okay, due to high temperature, diffusion process got increased, and due to this diffusion process, your wear is increasing. So that is primary responsible wear for created wear is diffusion. Okay, it is given there in the slide because of high temperature dropping, diffusion starts and the diffusion goes on increasing and where it's primarily responsible. Okay, created wear. Just give it slides also from that slide. The Taylor's tool life equation that is related to C is. So it is the intercept at speed axis is like this, okay, and this is your C, this is your V. So this is again intercept on C axis is correct. It is intercept on speed axis is your C, and this is your speed axis. Okay, there will be C corner. This is the C point is correct. Intercept of tool life axis is wrong. So this is your tool life axis, and this is again different. This is your tool life axis, and this is your VC. So intercept on tool life axis is wrong. You know the slope of the plot is again wrong. This is not a slope of the plot, it is actually n. Okay, n is the slope of the plot, it is n actually. And the intercept at full axis is 2, this is your 2 axis. So this is again different. Constant, and it is just a constant and a cutting speed at for 1 minute of tool life. Okay, this is again correct because what is your C? If you put t is equal to 1, then v is equal to t raised to n, which is equal to c. So if we put this t is equal to 1, so what we will put here? We put this t is equal to 1. So what is equal to? Our equation will become 1 raised to n. So anything you are put in 1, it will be anyhow 1 only. So v is equal to c. So it is the cutting speed for 1 minute of tool. Okay, this is again correct. Okay, because if you put it, it will give the answer. So what is the correct answer? 1, 4 and 5. So this is the correct answer. 1, 4 and 5. Okay. Meeting expression. Tool life reduces for rake angle larger than optimum because they is from the rake angle of of the chipping of the cutting edge. What you are doing actually here? Consider that this is your rake angle. What you are doing? You are reducing the rake angle larger for optimum. Your life reduces for rake angle larger than the optimum. What you are doing when going goes on increasing, your rate angle goes on increasing. So what happens? Consider the situation now. You are increasing beyond optimum. So this area available for uh, the actual cutting will be very less. So chipping off the cutting edge is work. In the 2 days gets vacant is again because the area is less. The chipping off may be possible. The tool edge gets weakened. Cutting force acting on a tool increases. No, this is for optimality. It is not a concept. It is goes on decreasing of the strain hardening of the workpiece material. No, there is no concept of strain hardening here. Optimal of larger temperature accumulation. Okay, again the concept is if the area is less, the temperature accumulation will be more. Okay, because there is a less absorb the temperature. Okay, so to which these tools are this is wrong, and the strain hardening of the this material again is wrong. There is no workers of strain hardening over there. Okay, the cutting rate. So this is your answer. So your correct answers are 1, 2, and 5. Choose one. I think these options are incorrect. Okay. So this is the B option is correct. So we have a problem now. In a turning operation, high speed steel tool, a cutting speed of V is equal to 90 meter per minute. Is used by the Taylor life equation has parameter A is equal to 0.120 and C is equal to 30 when the operation is conducted dry. When a coolant is used in operation with the same cutting speed, the value of C is increased by 10%. The percentage increase in tool life. So what at with the dry at for dry condition it is 90 P into 0.12, okay, is equal to 130 and T is equal to 130 by 90. Okay, so this T will become there 1 bar. Okay, this is 0.1 and the answer will be simply 1.444 raised to this 8.333. This is divided by 0 just. Okay, so your answer will be here 21.42 minutes. Okay, so you got T first, that is 22.42 minutes. Okay, so you got first T here. Okay, so let me write down here. So you got that your T is 22.42. Okay, first in minute. Right now you go for dry condition. Second condition, wet condition. Okay, yes, this is your T. Yes. Right now we go with the second condition, which is the with coolant condition. So with coolant, what do you have? With coolant, I told you already that with coolant we will just do the same thing. That is with coolant, what we will do just what is changing here? The C is increased by 10%. So what is C increased by 10%? That is C will become that is 130 into 1 plus zero point 0.1. Okay, that means your C will become 130 into 1.1, which is equal to 143. Okay, then calculate your T now. So it will be same equation, that is 90 T raised to 0.12 is equal to your 143. Okay, so when find T is equal to 143 divided by 90 raised to, you have the 1.02. Okay, so is equal to, I just solve further. It will be 143 means if you do simply like 143 divided by 90, it is same again. Like what we have 8.333 333 and your answer will be 47. Okay, 47, just calculate this, it will be 47.40 minutes. Okay, so we write down the second one also here. Your T1 in case of T2 your 47.40 minutes. Okay, so we have everything right now. So what we have to calculate a percentage increase. Okay, so how we calculate percentage increase? Simply you get your simple calculations amount increase. So divide it, subtract it and divide it. Okay, so how we will calculate it? It's again simple. Percentage increase we need to find out. Okay, so how we will find out it? It will be simply 47.40 minus 21.42 divided by, it is 21.42. Okay, therefore this is equal to 1.21, which is again equal to 121%. Okay, so this will be your answer. Okay, 121% is your answer. Okay, right. 20. Rule life test in and turning operation in the following data. So what is the data we have here? Rule life test. So we have your v1 and t are the value to calculate exponent. Okay, it's again very simple. So we have first equation is equal to 100 into 10 raised to n, which is equal to your constant, and we have your second equation. It is 75 into 30 raised to n is equal to c. So we know both are equal to c. Therefore, what we can do here, 100 10 raised to n is equal to 75 30 raised to n. So apply log on both sides. Ln 100 plus n ln 10 plus, plus is equal to ln 75 plus n ln 30. Okay, so what it will become, the 4.6052 plus n into 2.3026. Okay, this is equal to, the bracket, which is equal to 4 point, uh, equal to 4.3175 plus 3.4012 and get this value. If you get it at n on, that is not a problem. So what we will have, 4.6. Here we have written multiplication and keep bracket in anything. No problem. It okay, so keep the n terms on one side, keep the normal constants on the different side. So minus 4.3175 is equal to, keep the n term in one side, so we keep bracket at one side only now. So it will be 3.40 minus 2.3026 bracket into your n. Okay, we have that n, so it will be n is equal to, just calculate the direct calculation can do. So 2 sevens and 187. It is equal to, which is round up to 3 decimal points. So what, how do we do? Simply 0.261 is again equal to 0.262. This is your answer. Okay. Go to 10th question now. So the Taylor's two lab equation is given simply. So we have Vt raised to 0.2, which is equal to 200. We have everything. And what does the problem do? It is loading meter per second. Converted into meter per minute. That's what the concept. So what we have? V is equal to 1 into 60. So 60 meter per minute. You will have your V. Okay, so we have your V. You have your T, which is 0.2 into 200. This is your constant. So your T is equal to 200 divided by 60. Again, this will go to this side. So your answer will be 411.5. Just calculate. Your answer. So it's very simple. Okay. So your assignment is completed here. Okay. So this is the thing. Okay. Um, okay. So this is the thing. Okay. This is the, so everything is solved here. So we right now go for our practice problem sets. Okay. So this is the first question for you. This is in which method of the holding the work in lathe machine the two centers are used. It is actually same kind of question is in your assignments. So in faceplate we don't have two centers. It's a very simple thing. That's we don't have two centers. In dog plate yes we do have. In collet we don't have. So the answer is simple here. Okay, so in dog plate only we have two centers holding the work. Okay, we have like one center we have here. Okay, then center we have here. Hold. Okay, like this here we have a job. The left job will be here. Okay, like this. Okay, so this is the dog plate. In these both of the cases it's not possible. It's not there. So the answer is dog plate. Okay. Process in which cutter axis is parallel to the surface being machined is called as what they have as the cutter axis is parallel to the surface being machined. So it's peripheral. Okay, it's simple because in peripheral only your axis is this is your milling cutter and this is your workpiece which is downwards. Okay, here your workpiece. What they are asked here, your the process cutting the axis is parallel. Okay, to the surface being machine. Okay, this is your axis, this is your workpiece, and the axis of your work is parallel. Okay, both are parallel. This is not exaggerate, but exactly both are parallel. Okay, both are very parallel. So it's peripheral. Okay, so in face milling operation, the cutter edge are available on. So you know what is face milling. So in case of face milling, the cutting edges are available on lips. Again, the lips is not used in grinding. It is used in drilling. So, you know, this is usually in drilling process, not in grinding process. The end of the cutter, yes, we have. Outside the periphery of the cutter, yes, we have. That is both on the outside. Okay. So what is the correct option here? Is this because it involves both. Okay. So as it involves both the end and outside of the periphery of the cutter is your correct answer. Okay. In which operation width of the cutter is less than a workpiece width? Peripheral milling you know, slab milling you know. In slab milling it is not because it is mostly equal. Peripheral milling again this type of slab milling, so it's again equal. Slotting, end milling, there is drilling, so slotting it can be a so this is answer. Slotting we know how we do slotting. So, you know this kind of and we have only one this kind of tool we have and so this is how we do the slotting. Okay. So which part is getting machined? So you know this part is getting machined. This slotting, so it is called slotting. So slotting will be correct answer. So in which operation diameter of cutter is less than the workpiece width? Then what we are asking diameter. The previous question about width. Right now the diameter of cutter. So diameter of cutter means it must be end mill. Okay, because diameter of cutter is less than workpiece width will be the end mill. Simple. Slab mill you know already. It is like peripheral and both of these not also and slotting is again you know it is not about slotting it is about the width. Okay. The slotting width have width. But and here we have diameter. Okay, so it's simple. Okay, we have diameter over here, so that will be 8b. Okay, so this 8b is the correct answer. Okay, which of the following is not characteristics of milling process? The chip thin in the beginning and increasing the thickness is correct because you know the way chip is formed. So this is the kind of chip we form okay, in kind of milling. You know what is of milling right now. So this kind of chip will be we get. This is the point and begins with the point and ends with increases thickness. Okay, begins with point, ends with increasing thickness. But this has tendency to pull down. Yeah, is again correct. Okay, this is correct. You are of what you are doing. You are doing up milling. So in up milling, if you know the way this is this kind of chipping. Okay, the force upward force is applied. So it has a tendency to pull the work. Okay, this way. Okay, exactly the chip is shown. Exactly in that way, the material may be pulled down. Okay, so clamping is required. Tool engagement is not affected by surface characteristics. Okay, tool engagement is not affected by the surface characteristics. Yeah, in case of like scaling is happen, the tool engagement does not affect because it don't have any effect. That mostly this is not affected by the scaling or anything. Why? Because the what we are doing, we are going from like thin part and the scaling is generally on the upside not on downside, so if you scale up down milling it is a problem, but in up milling we are going from this thin point to that so to this point, so it will not affect much. Chip can be carried away from the newly machined surface leaving tool surface finish. You know this is wrong because in case of up milling this chip will can fall down on the new machine surface. You see the up milling process simply this can fall down on the newly machined surface. Okay, this may fall down on the newly machined surface, like that. Okay, this may fall down to my newly machined surface. So, taking away from the leading towards good surface finish is wrong. Okay, okay, this is the so tool engagement is not affected. This is correct, and chip thickness can be carried out away from the newly machined surface. This is wrong. Okay, okay, this is the chip thread can be carried away from the newly machined surface, leading for good surface finish. Okay, this is the correct answer. That's it. Which of the following is not characteristics of down beating process? So, cutting start at surface where the chip is at its thickest. Yes, it's the case of down. Okay, it's down, so it is correct. High impact force required for rigid setup. Yes, yeah, because as the thickness is high, this is this thickness, so chatter will be chatter is just actually because impact is high. Okay, what will happen? Impact is high. Impact is high. Okay, high impact forces required in setup. Cutting force tends to push the workpiece down and reduce the damping requirement. That is correct. Suitable for workpiece with hard abrasive scales as it is not work better. Okay, in this case also we shown you what we shown you here. Okay, this tool engagement is not affected by surface characteristics. Means it is not affected. Yeah, in this case it is not affected. If it is not affected concept is correct here. Okay, but here on the scales it is present. So how the downwinding is happening? We are directly go to up to this thickness directly. Okay, you know that thickness we directly go in. So what happened due to that thickness? And hardening or substrate, this is the hard material actually. This is scaled, so it is actually hard material. Because of this hot water meters. Okay, this will be hard material, and due to when it is have impact with hard material, so it will naturally it will tear out. Okay, it will be chipped off. So this is concept is wrong. Okay? Suitable for work is with hard abrasive scales. So this is wrong. The excessive tool work is correct because again the main concept is what we are doing. We are having this much thickness, and this is going like this. So this is our motion. Right? This is our motion. So due to everything is happening due to this only. Okay. So due to these things only everything is happening, and due to this thing the excessive tool wear is isn't there. Okay. So, so this is your correct answer. This is not. What is major problem in down milling operation? So less impact forces. We just few minutes will take talk about it. Is it less? So simple answer it is no, it is not less. Less shatter. It is yes, but it is not a problem. Less shatter is correct, but it is not a problem. Negligible to wear it is not again case. It's not again a case. Negligible to wear is nonsense. And if not clamped properly, the workings may throw towards the operator. Yes, it is a actual problem. Okay? So all the rest of the things is not problems. Okay, all are not problems. Okay, these are not problems. This is only the problem. Okay, okay. So this is your answer. In each of the following manufacturing process, the feed is not provided. In drilling, feed is there. In milling, feed is there. Turning, feed is there. Only poaching, because in poaching what we have? We have teeth. You know, teeth are having feed already. Okay, teeth are actually having feed. Okay, so feed is not provided there. That's simple. Okay, what's happened due to this? The feeds, this feed is not provided. Okay, feed is not provided here. Okay, that's simple it is. Okay, choosing a good answer. So which of the following is not advantages of broaching operation? Good surface finish is yes, it is. Close tolerance and it is variety of work shape possible. Yes, it is. Cheap and easily available tool is highly not possible because it is costly actually. Okay, broaching is costly. Okay, so cheap and easily available is again wrong. Okay, it's too costly and take time. Okay, so this will be your answer. What because what we have asked here, which is not the advantage of broaching tool. So this will be the answer. This is not advantage of broaching tool. Okay, which of the following is hard particles used in grinding process? So that is a problem that might be is or are. You need to think about it. Okay, so Al2O3 use yes, use BS4 use silicon carbide, silicon carbide. They all are used. So is the correct answer. All of the above. Okay, is the correct answer. All of the above. In which of the following process the abrasive particles are used for grinding? Okay, we are honing, we are using lapping, we are using super finishing, we are using polishing, we are using buffing, we are using. So simply it is honing, in distance we are using honing. In lapping again for higher surface finishing, super finishing again for higher surface finishing. Because in mostly we are using here, we are using loose abrasives. So we are not tight, so we are using loose abrasives here for super finishing. And in polishing again, we have abrasives. Buffing also we have abrasives. The abrasives are there everywhere. Okay, this thing where abrasives have. So it is all of the above. Your correct answer. Okay, all of the above. Which of the following are parameters of grinding units? So wheel grade, okay, wheel is written, so wheel grade is bonding material. Yes, it is again. So grain size, yes. All of three, all of three are actually your parameters for branding it. Okay, all of you to be correct. Okay, which of the abrasive is preferred for high strength materials? You simply give it in your slides, but just question that what can we use for it? How what can be used for high strength materials? Because mostly you can use diamond also. It is not a problem, but it will be highly expensive. That you are using too much cost. Like your pen will cost like 1,000 rupees. What's the use of it? Just 5 rupees. So you have to be optimal like that. Okay, so must be optimal like optimal cost. It should be optimal costs. Okay, so what will answer here? Aluminum oxide because yes, we are using high strength material. If it is like high alloy like carbon glass or ceramics, it will be silicon carbide. Okay, but what we have here just high strength material. So this is only your answer. Okay, okay. Each of the averages preferred for high strength materials. Aluminum oxide is the correct answer. Okay. So okay, which of the averages preferred for very hard materials like glass, ceramic, etc. So what we will use? So we have ceramics now. Can you use carbide? No, you can't use carbide. Okay. Glass and ceramics, carbide like structure, you can't use carbide. You can use ceramic, yes, you can use diamond, yes. So it's both. So both are can be used. Okay. Here the question is different. Here the question is different. The set is completely different. Okay. Here only one answer we have, but here we have both answer also. So both answers correct. That is the beauty. So you have to be very crucial while writing everything. Okay. The way the question is formed, you have to answer correctly. Okay. Both A and B will be your answer. Okay. The sieve number Sn corresponds to number of opening per linear what? It is foot, millimeter, meter, or inches. So foot is very big unit. Millimeter is not used. Both are not used. Is only used because this is American standard. This is American standard. Okay. Okay. In American standard, this is where SI used. So this is not only used. So you are having the inch here. So this is the concept. The American system. In which sieve number the average particles is 550. Appropriate it would be. So sieve number is 550. You know from 2 to 220 to some 600. What is this range? No, it's verified range. So the answer is verified. Again simple. Okay. If the sleeve number of abrasive particles is 550, what is the average diameter of single abrasive particles? Just calculate it right now with this question. You know what is your DG? 0.6 by sleeve number in inches. Okay, so this given. So your DG will be 0.6 into 550 equal to 1.0910 inches. Okay, and what we will do now? Just divide it by this 2. What we will do? Divide this by 39.37. So what will be answer? It will be your direct PG. So your PG will be 22.71 raised to minus 6 millimeters or meters. Meters. Okay. You just need to divide it. Okay. So if when you divide it by 10 to minus 7, you will have the answer. Okay. So It will be 21.7, okay, in micrometer. So if C number of abrasive particles is 20, what is the average diameter of single abrasive particle? So again, you know what is your dg. So your dg is equal to again 0.6 divided by Sn is equal to 0.6 divided by 20 is equal to 0.03. Okay. This. So what it is in inches. So what we do, convert it into meter. So we have this right now. We do convert it into meter. So what is your answer again? It is 0.03 divided by 39. I already tell you. Okay, 7. So what is your answer? 762 micrometers. It actually micrometers what? 2 minus 6 meters. So this is 762. This is 27. So almost 100 times more smaller. See the slew number and relation. Okay, 762 is the correct answer in meters. When work material is hard, the grain wear out easily, and the sharpness of the cutting edge is quickly lost. The phenomenon is called as. What will happen when the edge will become like sharp, blunt, like due to rubbing, constant rubbing? What will happen? The shear will become blunt, and what next happen? It will be glazed. Means shiny surface will be happen. Okay, shiny, which is called as like shiny surface will be happen, and that shiny surface is called as glazing. Okay, it is actually glazing. So shine will happen, and this will be shiny. No, it will be called as grinding, glazing. Okay. So wheel loading is different due to chips. This is due to chip boring is different, and wheel glazing is it is shine. Okay, due to the shine, it is have a glazing effect. Okay. Due to what why you got shine? Due to rubbing action. You know, due to rubbing action, it got shine and it will be glazed. Okay, wheel glaze. So this is your correct answer. The wheel glazing. If the grade of the grinding wheel is S, then what type of grinding wheel it is? So you must know that is there is a different that is like medium is different and soft is different, medium is different, okay, and your hard is different. Okay. So you know what is the way that is from A to H it is somewhere. You must know this. This know it is there inside. But, uh, so S means it is came in Q to Z range. The Q to Z range is for hard. Simple. So for hard means this will be your hard material and this is your answer. The hard. Okay, so your answer will be hard. So hard is your answer. Okay. If very hard material is needed to be ground, what grade of grinding will one must prefer? What here we have very high material is to be ground, so material is very hard. So what kind of material grinding we must have prefer? So here we are talking about grade. What you are asking? Grade that we are talking about. We will get to the letters like this. Okay, so these are all letters mentioned there. So what it is mentioned? Very hard material. So what is the concept of very hard material now? And grade. So simply grade will define what can be defined case. Grade will define the for hard material. We have very hard material, and what we will do for case of get of that material it is your grade. You go with softer wheels. What is the softer wheels? Who will do the softer wheels? Just to see. So what you need for very hard. So if you have softer wheels, what will happen? Your abrasive wheel is getting blunt, it is tough because of this is a blunt. Okay? Blunt grain. It is getting shift off. Okay, there is a big shift away and a new grain will come into that. Okay, and we'll have a new grain. Okay, what? Okay, this should be the concept. So the answer is B. Okay, the answer is C. Okay, so if the voids are too small for the chip, the chip stay in the wheel, not in the void. This phenomenon is called as. So what this phenomenon is called as? No, it's called as glazing is not option. You know, is that rimming is a process, and boring is again a process. So what we have? If loading is correct answer, which is formed due to chip accumulation. The will happen due to chips accumulation with loading. With loading is the correct answer. If very hard material is used to be ground, what structure of grinding will one must prefer? We have very hard material, so we need to go with what? Load structure. For what? For extra hardness. So we have extra hardness means more hardness means very hard. Means very hard material or very hard material. Okay. Extra hardness means for very hard materials. This is the concept for very hard. Okay, so for very hard. So this uh, what is this concept for very hard material? We need to have a closed structure, so it will add give you extra strength. Not hardness, extra strength it will give to you because of closed structure. Okay, and it will use you to get cut a hard material. Okay, so what it will give very hard, you get extra strength. Okay, you get extra strength there, and you can do cutting properly or grounding, grinding. Okay, right now what we want here, grinding is over right now means what you are grinding. The hard material grinding is over. So what now what we have? Your very good surface finish. Okay, in grinding operation. What structure of grinding will one must prefer? So if you have if you want very good surface finish, you have equal structure. That is more number. So it will be 15. As it is open structure, chip will get accumulated there. Okay, chip accumulation is good. So to it, surface finish is good. Okay. Okay, so this will be the answer. Oh, yes, because it goes to everywhere. Okay, each of the following is most commonly used in word in language. You know, yes, mostly you know the fact it is petrified. Most commonly because it is commonly we have rigidity also and strong also. So it is enough strong, enough rigid. That's why we go with petrified bond. Okay, so petrified bond is the answer. If very hard material is need to be ground, then which bond is used in a grinding wheel? Okay, you know the you right now might that time you know the concept of what you mean by very hard grinding. Okay, so very hard material means what you need for very hard material. Your chip will be or your grain should be dislodged. Okay, it should be dislodged, it must be removed. Okay, removed by cutting force. Okay, cutting force or force which is applied. Okay, it must be removed by a cutting force. So due to which new grain will be appear. Okay, new will grain will appear and new grain will appear and that new grain will start your grinding option. Okay, you will start grinding. Okay, so in this case, which will give you the that kind of softness. So the softness, the element which give you the softness can be used here. Okay, the softness concept, the bond which give the softness will be used here. Okay, so which bond do you get the softness? Okay, silicon bond. So these bond give you the kind of softness. Okay, so with this softness, what will happen? With this softness, what will happen? With this softness, it may be removed. Okay, what who will be removed? Abrasive. What is grit can be considered? It is abrasive particle. The grit can be removed. It means not grit. Actually, the blood grit can be removed. Okay, the blood grit will be removed and it will be replaced by a new grit. So your cutting process will be restored. This cutting not process is actually your grinding process will be restored. Okay, this restore means will have a less force and good material removal also. Grinding process can be restored. Okay, grinding efficiency is simple. Okay, so you will silicate is your answer. If if one need to perform a parting of operation with blue surface fish on a face, then which bond is used in grinding with? So right now what we need to do? We need to perform a parting of operations. So what parting of operations you know like you have some kind of cylindrical block and what here you to cut it from here. So what we do? Parting of operations. So what we need here? Simply what do we need here? A thin surface. What do you need here? A very kind of thin surface. You need. Okay. So which kind of bond will give you thin this kind of thin part? Only shellac bond. Okay. So as the shellac bond have capability to give the thin kind of structures, so what we will use and also have some kind of elasticity, you know. Okay. So elasticity also so we will go with the shellac bond. Okay. As it is providing these properties like it can be molded into thin part with elasticity also. Okay. What will happen to this elasticity part? It can go up to that. Okay, it can go up to this length. Okay, because it must have electricity also. Because it travel completely here. So for that case, it have both, that is thin plus elasticity. So it can be called by shellac bond. So shellac bond is your answer. Okay. Metallic bond is for diamond, rubber is not. It is not used. So the answer is just this. For diamond grinding wheels, which bond is used? Is again important question, that which bond must be used for grinding wheel operations. When we use diamond, so diamond is extremely hard material, hardest material on planet. So so for grinding, finding those cases, we can only go with metallic. It is there, it is only metallic. For diamond, what we have only metallic. It is mentioned this way, only metallic bond. So we can go only metallic bond. And carbide is to be ground in an external grinding operation to obtain a rough surface finish. The most appropriate grinding wheel for this purpose is. So what we have want here? That's again a question. It's what you want here. If you solve that question, your answer is solved. What you want is important question here. Obtain a rough surface finish. So what do you mean by rough surface finish? Your grains must be coarse. Okay, and what is the material? Carbide. What will go with? A is your aluminum oxide. This you can't go with A now, so your A option is cancelled here. So what is our C? So C is correct. So directly we can go with A. Diamond is like very costly. Okay, so don't go. You can't go with this. Okay, very costly and snow. You can't go with this. So your A is gone. Your this A is gone because A you can't go with carbide. Okay, we can't go with carbide here because of this A, and so uh, what we have left only C, that is your CIC. SIC will have, and your SIC will be this. Okay, this will be your SIC. Okay, so this will be your answer. Correct answer is actually because you can't use A anywhere. Here T is expensive, so only the answer is C. Okay, from one step you can, because there are small things. Again, what you have here, you have coarse grain is what you will do for coarse grain. Okay, you have 34 C number. That means again a coarse grain. You are going with rough machining. You have coarse grain. Here, what is the problem? 220 is very fine machining, grinding, very fine. So we can't go here. So 34 is correct. And again, for it is as it is rough grinding, so we have structures again in that similar concept. We everything is kept in that concept here only. Okay, so this is the correct answer. Again, your tool hardness and your bonding material between bond shellac is used again. So again, shellac bond is used to see why softness. No, I told you. Yeah, I told you here. The softness is there. Okay, the softness is there. And shellac bond. So again, the shellac bond is three again. You are using kinds of dense. Okay, and you are using S here again. So again, you have Q, a Q. We have. So then again, it is hard wheel. Okay, so every this like this C and your this T is can be give you what kind of thing we can get from this rough machining. First, rough grinding you will have here, plus for hard material. Okay, this can be done by this wheel. So both, that is carbide, it is hard material and rough grinding. So both is satisfied by this. Okay, satisfied by this. Okay, So we go with this answer. Okay. Okay. And the given answer. Okay. Again, we have a single problem for that. Again, what we are using? Ferrous alloy. So you can't go with this C, you can't go with this D because it's ferrous alloy. It's simple. So we go with A only. Okay. Not here. Yeah, we go with A only, but mostly this is the answer. Again, what we have? Very fine. So with what we do very fine. We have Fe, so we can't go with CED. So this A is again, but this finishing is very high here. Okay, so what will go with? Vertified bond, rubber bond again, it is not used. Vertified bond again, we have surface finishing, we have 16 here, we have 15 here. Okay, again, this is concept. We have T, so again, this is kind of hard tool, digit tool. This is soft shell. So this is kind of rigid tool. So this is only to satisfy. Okay, this is only satisfied. Okay, so only with this. Okay, this is what concept that we should understand. What are the concept that we must apply here? We have ferrous alloy that must be aluminium here. Okay, so okay, so we have must use the aluminium. Okay, why? Because it is not that much. Because again, I told you what is the main most important concept that you must go with optimum cost. That's it. As a manufacturing engineer, you must go with optimum costs. Okay, in manufacturing. Okay, or production simply optimum cost you must have. So aluminum oxide will be the optimum cost there, and the 500 is very fine. Okay, fine mesh. And T is good thickness, and what we have with the 60. Okay, it's opened for that could matter, but by these three only you can say that it is what you can have here if you consider the materials. What you will have here kind of a hard strength plus very fine finishing. Okay, okay, so both the criteria are satisfied here actually. So what we can do, go with this. Okay, okay, this is the correct answer. So again, it is a given adaptation. The process demonstrated in the following figure is called as. Is it milling? So first of all, you should know it is not at all a milling process. Okay, it is not at all a milling process. So both of the first option, that is this, these are got cancelled. So this is not a milling process. Okay, and again, uh, these options are got cancelled. And horizontal surface grinding, vertical surface grinding. You need to check your axis. Where is your axis? Your axis is vertical here. So the axis is vertical. It is shown here. Okay, your axis is vertical. So see here, your axis is vertical. So if we have vertical axis, what it simply means, it's a vertical surface area. Milling is not again. Milling, it is discarded previously. And what is the horizontal grinding surface or vertical grinding? So here, how your axis is inclined is actually with vertical. You know this. It is with vertical. So as it is with vertical, so what we will do? It is vertical surface grinding. Okay. So this is your answer. So it will be vertical surface grinding. Okay. So the process demonstrated in the figure is called as. Okay. So what is this? This is not a horizontal surface grinding. Vertical surface grinding is not here because it is concept different concept here. So this is actually cylindrical grinding. So this again this concept are gone. This is actually cylindrical grinding. You know, out of this you need to find out. Okay, is it external? No, it is not external. This is what is it? It is not external, it is internal actually. So yeah, it is internal actually. Okay, so if it is internal, this is the only correct answer. Okay, internal cylindrical grinding is the correct answer. Okay, so the range of inclination angle of regulating wheel in external centerless grinding is, you need to find the range in centerless grinding. Centerless grinding is most important concept which is used for very thin and high length. Okay. Where we can use this kind of process where in which the clamping is difficult. Okay. In which case the clamping is difficult. Okay. In this case only we go with centerless. That is external centerless. Okay. In this case only we go with external centerless. Okay. Where clamping was difficult. So, so what is the answer here? Just three and between 3 and 5. So I mentioned here, okay, this is the answer is 3 and 5. So for explanation it is mentioned here. Okay? So this is the inclination angle here, and this is how it is. Okay, this angle it is inclined. Okay, for the feed, for a feed it is actually inclined, and why it is process is used, I told you, and why it is inclined for feed motion because there is nothing to hold this device. It is told already in the slides that there is nothing to hold this device. So how we can move it? By providing a feed to this regulatory field. Okay, and what is the range of it? 3 to 5. And what is the force that we cutting out further we have? Okay, this is the right angle what we ask for, which is 3 to 5 degrees. Okay, it is given here. So again, so how the field force is calculated in external center is grinding process after in that is your dr is diameter of regulating wheel and where is angular frequency, rotation frequency of rotating wheel and I is inclination angle. Okay, so we have everything. So how it is calculated? So we know the formula. It is actually omega by dr by 2 is its actual force and multiplied by sin theta is inclination angle. So what is in actual value? 6.5 omega r dr and I. Okay, so this is your answer. Okay. This is a field force which is acting in this direction. Thus, what will happen? Your this workpiece will move. Okay, this workpiece for this workpiece to move. Okay. So for that we are using this, and this thing is accompanied by this condition, moving condition. Okay, workpiece is moved. So your answer is this. You know, this 0.5 omega r dr sin. Okay. Okay, so this in this problem, what we have, the width of the chip is 0.9 millimeter and maximum chip thickness is 0.12. So we know width is there. Is B is given zero point 0.9 and maximum chip thickness, that is T1 max, is going to be is equal to 0.12 millimeter. So what we want to find out, the grinding ratio we want to find out. So how we find the grinding ratio is equal to Rg. What is your Rg? Rg here equal to V max, which is divided by 1 by 2, which is maximum, which is this is our B is equal to 0.9 divided by this is your T max. So 1 by 2 0.12. So what is your answer here? It's 50. It's calculated. It will be like 0.6 by 0.06. So answer is 50. This cancel. If the width of the chip is 0.8, 50. Got the answer. This 50. If the width of the chip is 1.85 millimeter and average chip thickness is 0.40, that will be grinding machine. Okay, what we have here? We have width of the chip. Okay, but what is the problem here? Actually? The problem here you to what's the problem that what is the problem here actually? The average chip thickness is given to you. What problem in previous it is given? Maximum chip thickness. So the maximum thickness is different. So due to what happened? We have to take half here, but right now we don't need to take a half. So the formula will change here. So it will be Rg is equal to your V max divided by T average is equal to what is the T average simply is half T max. Okay, so but we don't use it. Okay, so what it will be V max simply. Okay, so it will be 1.85 divided by 0.40. So it will be 30. So 12.2. I think the answer is go with 30. Okay. So what 36 question what do you have? Calculate the volume of chip if grinding ratio is 60, maximum chip thickness is 0.8 and depth of cut is 0.5 and the diameter of grinding wheel is 20 millimeter in millimeter cube. Means volume we need to find out something. So what is the formula for volume? You know. So here you know what you know. Volume of chip. What is volume of chip? 1 by 4 Rg T1 square max 3 by T. So we have everything. T1 by 4 we have Rg which is 16. We have T1 max which is 0.8. Okay, we are putting in millimeters, so that is not a question. Yeah? Into what do you have? D. What is your D here? Grinding with diameter. So 20. And your depth of cut 0.5. So just multiply. So what will be your answer? Just mention. Is 8.095. This is our answer here. Okay. This is your answer. Okay. So we go for 37th question. A grinding wheel of 400 millimeter diameter rotating at 300 rpm and 0.8 active grains per millimeter square is being used to grind an aluminum alloy. If the width of the cut is 15 millimeter, the number of chips produced per second is. So what we need to find out here is simple. Again, simple. The width of the chip is given. Number of chips we need to find out. So what is the formula for number of chips? We want to find out number of chips. Okay, so we'll do the number of chips. So what you can do? You know the formula, okay? R D N into width into your concentration into 60 because you are using uh, okay, and everything is in millimeters, so that is fine. So your pi is pi. D is 400 into 3000 into 0.8 because it is given millimeter square now, so we can't put in anything. So we have to put in millimeters on this. The RPM is again RPM and everything is put in same condition. So pi we have put 2 to T, 2 to don't put B actually. So what is your B? It is 15. So multiply here 15. So into 15. Okay. So divided by 60. So what is your answer here? 7, 5, 3, 9, 8, 2. This will be your answer. Okay. It's 9 actually. Okay. Multiply this 50 also. So go on slightly off track. Okay. This is your formula. From this formula, you can have the answer. Okay. So just put your the value in the formula and you will have answer. Okay. Let's check everything. Previous. So this is 2 is your answer. This round up to nearest integer fraction round up. Grinding wheel of 100 millimeter diameter, rotating at 410 rpm and 0.95 active range per millimeter square, is being used to grind a titanium alloy. If the width of the cut is 2.5 millimeter, the number of chips produced per second is. Again, you have to find number of chips, use the formula. You need to check everything out. Everything is correct position. That need to check, and if you check it, it's not a problem. Just check the formulas once. It's unit of the formula. Where this formula we have a unit, and once you have everything, that is what we have to write out here. What we are doing here, the number of chips are asking here. Okay, so it is equal to pi dn bc divided by 60 because we are rpm. So it is a pi 2.4 into d is 100, which is n 4000 into your b is 2.5 into 0.95 divided by 60. So your answer is 49742. So this kind of answer we will get. Okay. So number of chips per second, this much, this much number of chips per second actually generated in grinding. Per second, chips per second we are getting. But in this case, due to width is high, let's go for 75. 7 lakh chips are producing 7.5 lakh chips are producing per second. The way chips are producing per check. Okay. Here we are only restricted to 50,000. Why? Because of the titanium alloy. Hard material are using. Okay? Hard material. Okay, that's why. Here we have aluminum alloy. It might be a soft material. That's why you have these changes. Okay. So what we have in this question, that is question number 39. For surface grinding process with 10 meter per minute feed velocity. So what we have PF is equal to 10 meter per minute. Width we have width is equal to width which is equal to P which is equal to 8. Okay. So width we have 8 millimeter, and the depth of cut we have 0.07 millimeter. The material removal rate in millimeter cube per second. So what is the material removal rate? It's MRR. Okay. Yes, the your velocity is given in minute, and we want in seconds. So we need to check this. Okay, we need to convert it into seconds. So we need to formula. We need to divide by 60. Okay, so your MRR is equal to BBF into D divided by 60, which is equal to what is your B here? 8 millimeters, and your BF is 10 into 10 raised to 3. Okay, divided by 60 because it is a weight into your depth of cut. Which is the depth of cut? 0.07. So your answer will be, you mentioned 93.33 meter cube per second. Okay, so this is your answer. 93.33. Okay, you got that 40th question. For surface grinding process with 0.333. Right now it is in meter per second. To calculate meter per second. So this time you don't need the conversion. Simply, but you need to convert by 10 raised to 3 into whatever meter, but the time conversion is not required. So we don't multiply by 60. So we divide by 16. So what is your MRR again? You need to find out your MRR. So this is MRR is equal to same here D. As we don't have so minute here, so we write in seconds. So would be is mentioned is 5, and your left of cut will be, so left of cut is 0.02, and your VF is 0.333. So, and what will you find? What is this? 0.333 into 10 raised to 3, because you convert it into millimeters. So what is your answer? The 33.33. Okay, into multiply. Here is, so we want, and 33 will be your answer. 5 into 2 will be 10 here. So this will be your answer. So 33 into 33 will be your answer. Okay. So question number 41. What is the true in case of average force per grit FC? You have to calculate. Okay. So you have FC now. So does it increase with VF? So yes, yes, increases with VF. Increases by increasing depth of cut. Yes. So it is correct. It is correct. Increase by decreasing the RPM. So it will be increased by decreasing the RPM. Yes, it is correct. Increase by increasing the diameter of grinding wheel. Yes, it is correct. So simply the answer is all of above. Because everything is actually contributing. You know the from the equation that the professor actually taught during the slides. So from that equation you can easily find out that this everything is actually important. Okay, from that thing you can find out that this thing is actually important. So you must know that equation. What is that equation? So you know this, what equation that we have is equal to FC dash is equal to, or not equal to, FC is proportional to your U0 expansion into VF raised to some point 0.8 into D raised to point 0.4, and your RC raised to 0.2 divided by your N raised to 0.8, your C raised to 0.8, and V raised to 1. So if you, this is the formula that you have. So increase by increasing the F is much increased. So VF is in numerator, V and E is in numerator. So increase by increasing the field and depth, and your N and your diameter is in denominator. So it will increase by decreasing both of them. So by this equation everything is correct. So your answer will be all of the above. Okay. So by, if you know this concept, then your answer will be simply all of the above. So your all of the above is correct answer. Okay. You are mentioning the all of the above will be your correct answer. Okay. So in grinding, the specific energy decreases with increase in average chip thickness due to what? Which effect is actually playing the major role here? It is an important concept that what is the important factor here? You know, in the slides, the graph that we have, like this kind of graph we have. mostly this kind of graph we have like it is increasing. What is this will be UC and this will be a P average. With increasing P average, increasing P average, your UC is getting to decrease. Okay, increase some. What that effect is called and if, what actually due to which thing that effect is causing due to it is very thin layer. It is mentioned in the section that is thin layer. And what is that effect is called effect, the effect of the thin layer, which is material like an ideal material. And due to ideal material, what the force will be cut, it is actually G by 2 pi. It is very high. Okay, due to which a lot of amount of energy is required. It is power, high power is required. But hence, grinding specific energy is high. You know, in grinding, the specific energy is high. Why specific energy is high? Due to this kind of actions, the rubbing, throwing, and size effect. I told you the answer is size effect. Okay. The grinding specific energy decreases with increase in average chip thickness due to the size effect. Okay. It is mentioned by the researchers that what actually happening, why this phenomenon is actually happening. This phenomenon is actually size effect. Okay. So the size effect is the correct answer. Okay. In grinding, the factor contributing the high specific energies are. So, what are the things that actually contributing for the high specific energy that we need to calculate over here? So, what are the things that actually affecting your uh, grinding specific causes the high specific energy for grinding process? Size effect again I told you due to which the force required or for cutting is very high. Rubbing is the correct answer because mostly when your grinding process is starting, in the starting of the grinding process, what will happen? In the starting of the grinding process, what will happen? When your grinding process is starting, in the starting of the grinding process, initially start rubbing just okay, or the rubbing action is taking place. So due to that, again the your power will be increased because in rubbing your energy is used but material removal is not taking place as just rubbing and material removal is not taking place so with which your specific energy is high again in flowing the material removal rate is very less. Okay, here there is no material removal, you know, here it is less material removal. So this is one causing and this is also the material removal. All of these are actually causing high specific energy. Okay, so the answer for this question will be all of the above. Okay, so all of the above is your answer. This all of the above will be your answer. Okay, so in grinding under light loads, all the energy is consumed in. We have light loads now. In case of light loads, all the energy is being consumed in what process? Because as you told in previous also told that in the like when there is a no just at the starting there is no not sufficient force is applied so just rubbing is happening here just moving weight is moving and now this is the work is just rubbing is happening okay. So just light load I told you what will happen here only rubbing process will happen. Okay, this rubbing process will happen in grinding at the light loads all the energy is consumed in the rubbing process okay. So this rubbing process will happen. So this rubbing is your correct answer okay. In a plot of specific energy versus chip thickness for rough grinding, the value of exponent m is equal to. So you know that there is a plot. Okay, there is no so this kind of plot we have, and for that this is actually the slope. You know, as you see into Tm is equal to constant. Hence, what we are using is actually inversely proportional to Tm. So the slopes that we have here will depend upon is the work conditions. For it is mentioned that for cutting point 2, the m is equal to point 2. So it's almost like negligible. It's less. It's less for single point cutting tool. Okay, this is slightly less. And 0.6 is for rough grinding, and 1.2 is not possible. Okay, so 1.2 is not here. That's wrong. As I mentioned there, this point 2 will be used in case of this. Okay, so and your 6 will be used for rough grinding, and your 1 is used in case of fine grinding. Okay, for fine grinding processes, you have one value. Okay, why you have one? Because of everything like it will the ideal material है. For ideal material, the forces will be high. So for ideal material, forces will be high because again what? Why? Because you have dislocations. In this kind of rough grinding, you have dislocations, but in this kind of very fine grinding, you don't have much dislocation. The material is ideal. In case of rough grinding, it's like suppose if you have a rough grinding, what will happen? It will have dislocations, okay, or mostly we have defects, and that these defects are actually leading us towards less force. You know this fact. Less force and your value of the exploded is again less slightly. But these kind of distributions are not present in ideal materials. So what? So in case of ideal materials, is getting present. So your grinding process that your cutting process, what is the value of your cutting process is kind of ideal material that we have calculated. I already mentioned this previously just few minutes. Into g by 2 pi. Okay, so this is very high. This is very high actually. So as it is very high, we can't go with this. And this is actually happening in case of very fine oil, like fine grinding process. Okay, so fine grinding process this is happening, and so what is your concept? This your one will becoming one. Okay, what is your here? Correct answer will be 0.06. For what? Rough grinding. You are asking for rough grinding. Specifically, you have a rough grinding, and for rough grinding, this will be your answer. Okay, so this will be your answer for rough grinding. Okay, so 46th question. In which phase of wheel wear the wheel dressing is necessary? So first is actually rapid wear section. Then second is constant, and your third is mostly is material removal and material singular out racing. So this is next question. So this is the phase. Fourth phase doesn't exist. You know, phase doesn't exist, and in this case, actually, the tool is getting blunt or grinding is getting wheels are getting blunt. Okay, as it is getting blunt, so what will happen? You need necessity for. Okay, so third will be your correct answer. This third is your correct answer. What happened in phase one? for grinding wheel wave. So I mentioned that what happened in case of phase one grinding wheel wave, that is rapid wear will takes place. You know, the rapid wear will takes place in case of this, and constant wear rate is happen in second wheel, and this wheel and will happen in third phase. Okay, so what happens in first phase of grinding wheel where then rapid wear. Okay, the rapid wear is your answer. So what is true in case of grinding wheel where phase three? So what are the options? Wheel becomes dull due to loading and glazed. Yeah, it's correct. Because due to high wear rate, in third stage the tool will becomes dull, and due to loading also chip will be clogged and glazed. Okay, so glazed, which is all from why it is glazed, due to rubbing action. Because rubbing become glazed, and due to loading, due to chip it get loaded. Due to both of this will become well and chip, so this is correct. Okay, material removal rate is reduced and grinding forces increased. So material removal rate is reduced and grinding forces increased with what? It's like a rubbing action. Okay, and again this loading action. What will happen? Your material removal rate is getting used. So it is mentioned there that your MRR will be reduced. Your MRR will be reduced and the grinding forces will increase. Okay, and the forces will increase. Okay, so this is again true. Wheel dressing is necessary as in previous question we asked. Check that wheel dressing is necessary. Yes, the wheel dress is necessary. So we know the wheel dress is necessary. And means what is the option we will have? All of the above. Okay, so all of the above is correct option. Okay, so we have all of these are correct option because wheel dressing is necessary. Okay, so all of the correct option. Okay. This is your option. So all of the above is your answer. Okay, this is the last slide that we have. Okay, so your date for assignment submission would be next Wednesday. Okay, so I told you everything. Most of the questions are covered here. Okay, every questions are covered here. The assignment questions are covered here. So okay, so some